In this video, I'll demonstrate how to use the PESPointCharacterization feature in the AMS driver to verify that your transition state searches are successful and that you actually end up at the transition states. And as a starting point for this demonstration, I've already optimized the transition state with DFTB for this reaction up here. So what we have is a Claisen rearrangement, and I can show you the results of this here. So I have the left-hand side here with the double bond to the oxygen here, and then there's a reaction. And now there are instead two single bonds to the oxygen, and that's the right-hand side over here. And this is actually an intrinsic reaction coordinates calculation that I ran with DFTB. But then the goal for this demonstration is to optimize the transition state, so this point with DFT, and to also verify that it is a transition state. And the way to verify that you have a transition state is that there is exactly one imaginary frequency. So the method that we'll use is ADF for DFT calculation together with the 𝗬𝗏 functional, and that's from this paper here, which implemented this functional into ADF with Slater type orbitals. So we'll use a DFT functional, and then we'll use a transition state optimization. And for transition state optimization, it is recommended to provide some initial Hessian, either to calculate it or to provide an approximate initial Hessian. And I'll use this option called calculate with fast engine. So this basically means to calculate it with DFTB on the fly before the optimization starts. And then once the optimization has finished, I'll try to verify the transition state, and I'll compare two methods. The first method is to calculate all the frequencies, so that's quite slow. And that's sort of the naive approach. Calculate all the frequencies and you check that one of them is imaginary. And the second approach is to calculate only the lowest frequencies. And that's what you get when you enable this PESPointCharacterization option in the AMS driver. So we can look at the input. Here is the first calculation where I calculate all the frequencies. So I copied the DFTB calculated transition state at this point into AMS input. And I set up an ADF calculation for a transition state search using the 𝗬𝗏 functional, and I tick to calculate the frequencies, which means I'll calculate all the normal modes. And for the transition state on the optimization panel, I tick this initial Hessian calculate with fast engine, which means to calculate it with the DFTB in this case. And the input for the second option for the PESPoint character is almost exactly the same. The only difference is I unticked this option for the frequencies on the main panel, and on the optimization panel, I instead tick this characterize PESPoint. And if you prefer to see input files or run from the command line instead, for all the normal modes, you set properties normal modes yes in this block. And for the PESPoint character, you set properties PESPoint character yes here. Okay, so I ran the job, so let's view the results. So I can open this trajectory in AMS movie. And then we see that it optimizes to a transition state. So this is the optimized transition state. And the first part of this calculation is the same no matter which kind of post-processing I do. So in the case of the PESPoint character job, the optimization is exactly the same. So those are the same two transition states. But if I view this now in Spectra instead, so let's start with all the frequencies. Then we see we have one frequency with that has a negative or imaginary at -10 terahertz, like this, along the reaction coordinate. But you can also see I get all these other normal modes calculated as well. So I spent a lot of computational time to calculate all of these normal modes. And all I was really interested in this case was this mode up here. So instead, with the PESPoint characterization, I can open in AMS Spectra. And then we only get two modes, the two lowest lying modes, and then we see this mode is exactly the same and it's imaginary. So I only need to calculate these two modes to verify that I have a transition state. So let's compare the timings as well. I can do that if I select these jobs and I build a spreadsheet. Maybe I save it as comparison. Then we can see here in the elapsed time column, and we can compare these two jobs. So when I calculate all the frequencies, it took about 5,900 seconds, and for the PESPoint character, it took about 1,100 seconds. And actually a lot of this time is the initial kind of optimization, so the PESPoint character is a lot faster than calculating all the frequencies in this case. So the take-home messages here are to when you run a transition state search to either provide or to calculate an approximate initial Hessian or an exact Hessian to make the TS search more robust. Or 𝘂𝗲𝗵𝗵𝗁𝗃 is a good non-hybrid all-around functional. So it's not a hybrid functional, which means you don't have to calculate any non-local Fock exchange. And PESPoint characterization gives just the lowest frequencies. So this is a good choice if you only need to verify transition state or minima. It is much faster than calculating all the frequencies. But if you want to calculate free energies, for example, free energy barriers, then it's not a good choice because it doesn't include all the vibrational normal modes. So as a next step, if you want to continue with this example, you could optimize the reactant product to get the reaction energy and reaction barrier. Or you can also read more in the PESPoint character documentation that we have on our website.